is going to be an oscillator design or the design of signal generators, right? And along with that, we will be saying the mixer circuits also. So the first three chapters are devoted for the design aspect. Okay, the remaining chapters are more or less theoretical study, right? And the chapter number 4 is mostly the design of chapter number 5 is devoted for the different types of sources of electromagnetic interference. And finally, the last module, chapter number 6, that we are going to see about electromagnetic compatibility and how it is going to be an important aspect in the design of RF and electronic circuits, right? So before beginning to the module number 1, just let us have in general discussion of what do you mean by the filter circuit or the filter device, which is basically designed to filter out or to remove certain signals from the other set of signals. Okay, so for that I will be taking or I'll be making use of this online whiteboard, because some of the basic concept I would like to elaborate you by actually drawing it on the blackboard. Okay, so here it comes. Now what I will do is I will share my screen with you people so that you people can visualize whatever I'm doing on the blackboard. Okay, and you just tell it to me also whether it is visible to you or not. Right? Okay. So I will start recording. Okay, so here we go. Now everything is getting recorded, our video as well as the screen that I will going to be share with you people during the explanation. Right? Yeah. Okay. I hope the screen is visible to you. You just tell to me whether my screen is visible to you, because right now I'm sharing my screen with you people and it is showing the screen. Yes, is it visible? My screen is visible to you? You might be
Yes, sir.
visualizing my screen of a Teams app. Yeah, okay. So let us begin with the basic introduction of RF filters. Okay. Yes, my iPad screen is visible to you. Yes, please respond once again. Hello, student.
Yes,
Please
sir.
respond.
Yes, sir.
Okay, fine. Because I should know whether you people are going to visualize it or not. Otherwise, it will go in a wrong way. Okay, so first of all, let us elaborate the concept of microwave filters. What are microwave filters and what are their roles in the microwave communication? I hope the notes page is visible to you, right? It is. So basically, let us start with non-technical. I hope the blackboard is visible to you along with my handwriting. microwave filters. Okay, so microwave filters are basically the RF circuits which are particularly utilized for the purpose to separate out certain specific frequency component from the rest of the frequency spectrum. Okay, so for example, if you have the different frequency signals, which I will be showing over here with the different colors. This is a blue signal. Now let us say this blue signal has certain frequency f. Similarly, we have another frequency which is a higher frequency than this is say a second signal. Let us call this signal with certain frequency f, right? And let us take two more signals. This is another signal. Let us say f3, and let us take another signal. Okay, f4. So here you can visualize that four different signals I have shown on the screen, which are different in terms of their frequency range. Okay, so here F1, F2, F3, and F4, all they are representing the frequency component of these signals, and they are going to be different from each other. Okay, so for example, here, if we want to separate out all these frequency components by means of certain device. Now let us say this is a black box, and this black box, I should make use of it in order to filter out certain desired frequency component out of all these four different frequency components on my left hand side, right? So F1, F2, F3, and F4, these are the different signals which are different in terms of their frequency component. And out of these different frequency components, I want to select a particular frequency component. Let us say I am interested to filter out only a signal having frequency f3. Now for that, we'll be going to make use of a device, and that device we labeled it as a black box. Now this black box is nothing but a filter circuit. Okay, so this is a filter circuit. Now what this filter is supposed to do, the filter is supposed to take input all these frequency components together. Okay, so at the input of this particular filter, we have a broad spectrum of signals having different frequency ranges, right? And out of all these different frequency signals, we are desired to select out or to filter out a specific component of the signal. Now, in our case, let us say we want to separate out only a signal having frequency f3. Okay, so this job can be accomplished by using the RF filter or a micro. So what is our expectation at the output of filter then? At the output of filter, ideally, we should get only the desired output for which that filter is designed for. So here we normally, as this filter is designed to filter out a particular signal having frequency f3, we observe that at the output over here. Okay, so this is the output side, you can say this is the output side, right? This is the output side, and at the output side we have the signal frequency having frequency component only f3. So this is what we want to design a circuit using certain RF component and electronic component. Okay, and this particular circuit, whatever we call it as a filter circuit. So this is a filter circuit. Okay, so this is a basic concept of a filter circuit. Filter circuits are the circuits which are utilized to filter out certain component of the frequency spectrum. Okay, and the design of the filter is based on what particular frequency it is looking for. Okay, so the design will be based on that particular frequency component, right? So ideally we should get only a particular frequency component at the output. Okay, but in the time you will see ideally this is practically we will get certain minute amount of other signals diluting. Okay, so this we call it as a finite limitation of the filter circuits, right? So let us go ahead and see the another analogy of the filter circuit. Okay, say just I am taking some out of the syllabus presentation. So here let us say this is a person over here. Okay, so rather I will choose some different color. Student, you kindly tell me whether the write up is visible to you. Yes. Yes, student, kindly respond whether the write up is visible to you. Say
Yes, sir.
what I'm drawing is the face of a person. Okay. I hope that handwriting and drawing is visible to you. Okay. Okay. See what I have drawn is a face of a person. So what you observe here, what you can think of about a person. Okay, so this is a face of a person. Okay, and he has hairs, certain hairs, right? What can you comment about the hair of this person? Can you tell about how you feel this person in terms of presentation? Yes, student. This I have drawn a face of a person. Okay, and this person I have drawn with hair on his head. What is your observation about the presentation of hair on his head? Yes, you can respond to me. What you feel about the organization of hair, representation of hair of this person? Yes. Side by side, I will draw another image. Again, the same person, right? Okay. So if you compare these two persons, okay, this is as good as the same person. This you can say the first, and this is the second image. Okay, first image and second image. What you see the difference between these two face images of the person? Yes. Hello, student. You can respond to me. I want to know what is the difference of these two images of the person. What can you comment out? You can compare these two faces of the person and you can tell what difference you will notify here. Yes, students. Yes, anybody can reply. Hello. Hello. Yes. I hope my voice is drawn two faces of the person over there. By observing the faces of the person, what can you tell? Yes, anyone? Hello. Hello. Yes, student, you can respond. See, I have drawn that image over here. What you see over here, what is the difference between the two images? Yes. There is a difference. There is a lot of difference between these two faces of the same person. On my left hand side, the organization of hair on the head of that person is not well. So here, in the first particular case, in the first image, the person has unorganized hair. Okay, so the hairstyling in the first case is unorganized. While if you compare the first image with the second image, we see that the hairs are good or in a nice way they are organized. So the hair setting of the person in the first image is, we cannot call it as a setting, it is just unorganized or disturbed hair setting, we can say. In the second case, if you compare, it is nicely set, the second case. Okay. So how this can be accomplished? Here, what tool you will be using in order to organize your hair? Definitely the answer is a comb. Okay. So what is a comb? So comb is a device, right? So you will see, you already know what is a comb. Okay, we are using it daily. Okay, so this is a comb. So this comb is, we can call it as a device, which is used to organize the unorganized hair setting of a person. Okay, so this comb is rather acting as the filter circuit. Okay, so when you use this comb with unorganized hair, you can set the hair into organized way in this way. Okay, so that means it will filter out the setting of unorganized frequency component into certain organized frequency components. Okay, so when you use a comb with unorganized hair of a person, you can set the hair of the person in a shaped way. Okay, and you will get the second image. Okay, so here the purpose to tell you people that here the filtering job can be accomplished by using a device or by using the equipment, rather we call it as a comb. So this is just a natural example I would like to give in order to tell you the resemblance of the filter circuit with the natural object. So here comb is nothing but a natural object. Okay, and by using this natural object, filtering process can be performed. Now here filtering process refers to a process or to an operation of organizing the hair of a person. Okay, so this is just, I want to illustrate you the concept of the filter circuit in non-technical way. Okay, so you can consider comb as a filter device, which when used over the unorganized hair setting of a person, you can organize the hair in a nice way or in a represented way. Okay, so comb here, it is a device, and the same device we can call it as a filter circuit. So here the purpose of using filter is to separate out or to organize specific frequency component signal out of many signal components, right? So this is just the illustration example of the filter circuit, right? So we go ahead and let us see a little bit history of development of the filter circuit. So here I will write historical development. Historical development. Can anybody know when the microwave or RF filters were being developed? They are being developed in World War II. Okay. During the World War II, the development of RF filter or microwave filter took place. Okay. So originally there were few people who started working in the design of RF and microwave filter. So these people are Mason, okay, Sykes, Lawson, and Richards. Okay, so these are the name of research people who started the development of RF filter circuit during the World War II. So it is around 1930, you say. So the first deployment or the development of RF filter or the microwave filter was took place in the year of 1930 by a group of people who are collaboratively working. So these people are Mason, Sykes, Lawson, and Richards. Okay, and basically the prototype they came with the filter design is based on image parameter technique. So we will go into the details of this image parameter technique and how the filter circuits are designed using this technique. We will go into the details later on. So what they did, these people they came together and they developed the first filter circuit. Okay, and this filter circuit is based on the mechanism of image parameter technique, right? So this is the historical development. So actually the development took place in around 1930, where the World War II was just began, and these people they came together and they found that there is a need to design a particular circuit, electronic circuit, which will filter out some of the frequency component out of the given broad spectrum. So actually this was the need. So that's why they started designing this particular circuit. Okay, and the first filter prototype was developed by them, and the filter prototype was based on the principle of image parameter technique, right? So we go ahead then we would like to see how the filter frequency response look like. Okay, so we go to the next point, that is frequency response of the filter. So what do you mean by frequency response? I hope my handwriting is visible to you, right? So frequency response. So what do you mean by frequency response? As you already know, the low frequency amplifier frequency response you already studied in your second year, right? So you plotted the amplifier frequency response from some frequency to certain frequency. So in the same way, we are dealing with a high frequency. Normally it is ranging in the RF level, okay? So up to several gigahertz also. So frequency response of the filter can be represented in a different ways. So the most common way of representation of a filter characteristic frequency response is by making use of insertion loss versus frequency plot. Okay. So here we'll define what is that insertion loss, attenuation, propagation constant, and so. Here we will define what do you mean by frequency response. Frequency response of a filter is simply, we can say, it is a frequency behavior of the filter circuit. So the filter is excited with a certain input signal, and the filter is going to filter out some of the component from the given input, and it is going to give that signal at the output. So we are going to plot the input output response of this filter circuit, and which we call it as a frequency response of the filter. Now, a most common way to plot the frequency response of the filter is by plotting the insertion loss. We'll come to the terminology of insertion loss later on, but for time being, you just understand insertion loss versus frequency. So this particular plot of insertion loss versus frequency, we call it as a frequency response typically exhibited by the filter circuit, right? So what we do here on y-axis, okay, y-axis we normally call it as a dependent axis. We plot insertion loss. In short, we IL stands for insertion loss versus frequency. Okay. So what we are going to do is we are going to plot the insertion loss of the filter on the dependent axis, that is on y-axis, versus independent variable, that is the frequency component on the x-axis. Okay. So based on the insertion loss frequency response characteristics of the filter, there could be four different situations. Okay, and these four different categories or situations of the filter will classify the filter itself. So what is the classification of this particular plot? So this plot is classified as low pass response, right? This is the first. Second, high pass response, right? Third is band pass response. And fourth, band stop response, right? So how these different types of filter responses are represented by insertion loss versus frequency diagram. So that I am going to draw it now. Okay. So first of all, how we can show the low pass frequency response of the filter in terms of insertion loss by using the help of this particular diagram. Okay. So first of all, again, you need to draw y-axis and x-axis. On x-axis, we have frequency. On y-axis, we have the insertion loss. Okay. Now, for the low pass filter, I will choose a different color. Okay. So let us say I will choose this yellow color. Okay. And here, see. Okay. So this type of a response, I will make it get a little bit thicker so that we can visualize it clearly. So this type of a response, we call it as a low pass response. Okay. So here I will write low pass response. So opposite to this, high pass response, how it look like? High pass response look like this. Again, frequency and insertion loss. Okay. Now here it will be opposite in this way. Okay, so this is the frequency response of high pass filter. I will write here high pass response. I will elaborate and I will explain these responses in detail. Let me first draw all of them. Then third type is the band pass response. Okay. The third is the band pass response. So the band pass response is a combination of both insertion loss on y-axis, frequency on x-axis. The insertion loss characteristics will be something like this. Band pass. Okay. So this is the band pass response. And finally, the band stop or band reject response. So this is the insertion loss. Okay. So band reject response is opposite to band pass response in this way. Okay. So let us explain these filter responses one by one, based on which the filters are classified itself. So this is the band stop response. Right? Now let us go into the details of these filter responses one by one and elaborate them. So first of all, here we'll start with this type, that is a low pass response. Okay, so here I will highlight. So this is the first image that we are talking about, the low pass response. How the low pass response of the filter is represented in terms of insertion loss and frequency. Initially, insertion loss is low. So here, if you observe that our yellow line, that whatever we have drawn, it is starting from 0 over here. Okay, so it will remain near to 0 value. Okay, and at certain frequency, we call it as a cutoff frequency, FC. Okay, so once the signal crosses the cutoff frequency, the insertion loss value tend to increase over here and it will become very high. Okay. So initially when the insertion loss is less, near to zero, that means there is a no insertion loss. If there is a no insertion loss, the signal will propagate easily. So this we call this particular section over here where the insertion loss is minimum. So this particular region we call it as a pass band. This is called as a pass band. So why it is called as a pass band? From 0 to a frequency fc, the insertion loss value is minimum, which indicates that the signal can propagate easily. And that's why from 0 frequency to a frequency fc, we call this as a pass band. And once the signal crosses the cutoff frequency fc, we see that insertion loss is increasing. And this particular band, we call it as a stop band because insertion loss is now increased. And when the insertion loss, when it increases, the propagation stops. The signal propagation stops. So this is a typically stop band characteristics. Okay. And we see that from 0 to up to certain frequency fc, the signal will be propagated. So that means the signal in the low pass region, in the lower frequency band, it is getting propagated, while the signal after cutoff frequency is not propagating because the insertion loss is going to become too high for that particular filter when it crosses the frequency fc. So there you will find insertion loss will increase in the stop band. So this particular type of frequency response, we call it as a low pass filter response. Opposite to this, in the second diagram now, in the second diagram, yes. Yes, anybody want to ask? Hello? Shall I continue? Yes, anybody want to ask something? I heard a voice from someone. Shall I continue? Okay. Let us talk about the second image. This is the second image. Now what we see in the second image? In the second image, only the first type of response is now reversed. Now what we see over here, again we have certain cutoff frequency, right? So this cutoff frequency from 0 to certain cutoff frequency fc, the insertion loss value is very high. When the insertion loss is very high, the signal cannot propagate. That means a signal from 0 to fc for this second diagram will not propagate. And that's why from 0 to cutoff frequency fc, this band we call it as a stop band. Okay. And once the signal crosses the cutoff frequency fc, the insertion loss tend to become lower. When the insertion loss becomes lower, the signal starts propagating. And this band, when the frequency is greater than fc, we call it as a pass band. So what is taking place over here? What is the difference over here when it is compared to the first case? As compared to the first case, after the cutoff frequency, the signal is getting propagated. Okay. So only the positions of pass band and stop bands are getting reversed in this particular case. And this particular type of a response of the filter, we call it as a high pass response. Why it is called as a high pass response? Because every frequency signal or every signal which is beyond the cutoff frequency fc, all the signal can be easily passed by the circuit. So that's why it is called as a high pass circuit. On the other hand, if the frequency component of the signal, if it is located below cutoff frequency fc, that signal will get attenuated because of high amount of insertion loss, and we get a stop band characteristic. Okay. So coming to the third figure over here, it is just the combination of first two images. So when we compare the third particular case over here, So second case is over. Now we are discussing the third case. In this third case, we will be dealing with two cutoff frequencies, FC1 and FC2. Okay, so here I will write from zero frequency. From here it will start from 0 to FC1. The insertion loss is less. Sorry, the insertion loss is very high, right? Insertion loss is very high. In which particular range? From 0 to FC1. So this particular region. So when the insertion loss is high and it gradually reduces when you approach to first cutoff frequency FC1. So this you can call it as a stop band characteristic. Okay. From FC1 to FC2, there are two cutoff frequencies for this particular type of frequency response. So from FC1 to FC2, what we have, the insertion loss is low, opposite, right? And again, from FC2 to infinity. To infinity means to whatever further frequencies, all frequencies we can say. Again, the insertion loss tend to become high. Okay, so this middle band is a pass band, and after FC2, when the frequency again becomes higher than FC2, okay, so again this will be a stop band. Okay, so what we observe over here, we observe over here that a specific frequency components in the range bound by two frequencies FC1 and FC2 are getting propagated only. And this type of a behavior we call as a band pass response. That means a typical band starting with certain frequency FC1 to certain frequency FC2 that will only allowed to pass by the circuit. This type of a response we call it as a band pass response. Okay, and then finally coming to the fourth diagram over here, which is just simply opposite to third diagram. So what is this diagram? This diagram again represents the reverse behavior of the band pass response, and this is typically known as band stop response, or it is sometimes also known as band reject response, right? So here again we have the two cutoff frequencies FC1 and FC2. Okay, from 0 to FC1, what we can comment about the insertion loss? Insertion loss is low. And again from FC1 first cutoff frequency to FC2, the insertion loss becomes high in between the region, right? And from FC2 to the further frequency up to infinity, we could call it as a F infinity, right? Up to the whatever value of the next frequency, okay? The insertion loss again becomes low. So what that indicates? It indicates just the opposite behavior of the band pass response, and this particular response we call it as a band stop response. Okay, so this particular 0 to FC1, if the insertion loss is low, we call it as a pass band. Okay, from FC1 to FC2, as the insertion loss increases, this band will be stopped. Okay, and this is we call it as a stop band. And after FC2 to next infinite frequencies, again we have the passband behavior. Okay, so this type of response, which is opposite to band pass response, we call it as a band stop filter response, right? So here we saw in brief how typically the behavior of the RF filter look like in terms of when it is plotted with insertion loss versus the frequency. So the four main characteristics of the filter we saw over here, that is low pass response, high pass response, band pass response, and band stop response with respect to when it is plotted with insertion loss, right? So do you have any doubt in understanding the filter behavior? Yes, student? Now, you can focus on these frequency response characteristic, think on it, and you just try to tell me what other information that you can find out from these responses, which I have plotted on the screen. You just observe them carefully and you just try to tell me more about these types of filter responses, how they look like. Yes. Any idea what you think of? Any other information are you going to get from these filter responses? Or what is your observation overall about this frequency responses of four basic types of a filter? Yes, students? Yes? Yes, what is your observation over here? What additional observation you can make from here? Yes, anybody is there? I see over here that many people they have logged in, but I hope that they just left the channel, okay, by just leaving it on or yes, yes. Can you reply me? What observation you can make about this filter responses? What will be your additional observations? Now here the thing is that if you observe carefully, the stop band and pass band characteristics, whatever we have drawn, they are not sharp. Okay. So ideal frequency response should be a very sharp. So what do we mean by this? Let us see. For example, ideal frequency response of the low pass filter when you plot insertion loss versus frequency. Okay. So how it should be? It should be sharp. Okay. So I will choose some different color. Let us say I will choose a red color now. Okay. And let us say I will choose some, yes, we can visualize. So this is ideal response of low pass filter. Ideal response of low pass filter. Okay, so what you see over here, here we get exactly defined cutoff frequency. So the stop band and the pass band. So this is the pass band, okay, and this is the stop band, right? So pass band and stop band are definitely exactly separated with a single frequency component FC, or the frequency response plotted by taking into account the insertion loss is a very sharp. So this is a sharp response ideally we should get. Okay. So similarly, when we plot the high pass frequency response opposite to this, again a frequency versus the insertion loss. Okay. So how we should ideally get the frequency response opposite to this, right? So you should get a stop band initially and then a sharp cutoff and then you should get pass band response. So here you get frequency FC. Okay. And here again you can label it out this as a stop band and this as a pass band. Okay. And whatever we have drawn, right? So this is ideal response of high pass filter. Now, on the similar basis, you can draw the ideal response of the band pass filter and band stop filter also. So what we observe when we compare the actual response with the ideal response or the practical response, we observe that the cutoff or the transition from the pass band to stop band in practical case is not that much of sharp as it is expected to be. Okay. So actually we do expect that there should be a sharp transition between the pass band and the stop band for the filter responses, as I have shown in the second diagram with the red color, right? So this is the ideal response, anticipated response. But anyway, such a kind of a sharp transition from pass band to stop band or vice versa is not going to get in a practical situation. So what we get over here is the gradual response. So here I will I would like to call this response as a gradual response, right? So this response we call it as a gradual response. Gradual response means the response is not sharp and it will take some finite amount of time to make a transition from either the pass band to stop band or vice versa. Okay, so this is the practical situation. We are not going to get the sharp transition between pass band to stop band, but rather we will get certain time and we will get a gradual frequency response. Now, do you know why this is taking place and why we are not going to get the exact ideal sharp response? Do you have any idea why we are going to get the gradual response instead of this ideal sharp response? Yes. So this happens because of the loss of the signal component in the resistive part of reactive elements, which we will be utilizing for the construction of the filter. Okay, so we'll see details on it later on, why we are not going to get the sharp frequency cutoff response and why we are going to get its gradual mechanism of transition between the pass band and stop band. This is because the finite signal loss that will be taking place because of the resistive component of the reactive element which are used in the construction of the filter. Okay, so I hope you understood what is the basic terminology of filters, how they are historically developed, what is the physical significance of this filter. I took that example of neat representation of the hair of a person, okay, with the help of a comb device. And then we discussed about the four preliminary responses of the filter, and based on that how they are defined. Okay, so low pass, high pass, band pass and band stop response. And then we discussed about how it should be behave ideally and why it is not behaving ideally, the reason we also saw behind it. Okay, so if you have any particular doubts up to this particular discussion point of view, you can ask. Otherwise, we will proceed further. Yes, students, you have any particular doubts in this? So we go ahead and we discuss on the concept of periodic structures now. Okay, periodic structures. So let us go ahead with the periodic structures now. What do we mean by periodic structure and what is their significance? Periodic structures. So what are periodic structures? Okay, so we'll come to this point in detail technically later on. Try to define or try to reason out how we can accomplish the job of filter mechanism, how we can filter out certain thing from many things. Okay, so again we'll be showing you the example by taking the help of any particular natural example. Okay, so let us say this is a funnel. Okay, and you are going to pour some mixture, okay, into this funnel. So this is what a funnel, and you have certain solution, mixed solution you can say, and you want to filter out certain thing out of this mixed solution. We call it as a filtered solution. Okay, So this is a real life example how the filtering process or the filtering operation is going to take place, right? So what actually the filter or the funnel here, whatever I have shown, it is utilized for. This funnel is a filter device, remember. The funnel is acting as a filter device. And this filter is used to filter out specific part of that mixed solution and to separate out certain specific component. So this is specific filter, filtered solution, or you can call it as a filter component. So what we have here, we have a mixture of a solution, and out of that mixture of a solution, we want to separate out certain thing, certain specific solution, and that can be done with the help of filter mechanism. Now this is a filter circuit. So here we are interested in the design of this particular device, which I have encircled over here. So this filter is utilized to separate out a specific type of solution from that mixed solution. And this filter is designed on the same principle. Okay. So what do you think? How this type of separating out a specific component of the signal or the solution can be accomplished by using the electronic circuit? How the circuit will come to know which component it has to filter out of the many given things. So this is the principle of design of the filter. So the principal design of the filter is based on certain primitive structure. We call it as a primitive structure. Okay. So here I will write primitive structure of filter. So what is the backbone, or you can call it as a primary or primitive structure of filter circuit? So the primitive structure of the filter is nothing but the periodic structure. So what do you mean by periodic structure? Can you give me any example of periodic structure that exhibits in the nature? Any particular periodic structure. For example, in terms of a transmission line theory, let us take this as a transmission line. We all know that this is a transmission line, two-wire transmission line. Okay. So this is a simple transmission line, right? Okay. Now this transmission line, what I'm going to do next is I'm going to load this transmission line with certain reactive element. Okay. So these reactive element, what I will do is I will show with certain different color. Okay. I will choose this yellow color. So what I'm doing here, I'm loading the transmission line with certain reactive elements. You know reactive elements, inductive and capacitive effect generating. Okay. So what these are known as? These are reactive elements, or you can call it as a reactive loads. Okay. So what I am going to do, a plain transmission line I am going to take, and that plain transmission line I am going to load with reactive loads. Okay. And how I am going to load the reactive loads onto this transmission line? I am going to do it periodically. Okay. So this is very important. So this is a certain length, say delta L. Again, I am going to load the transmission line with the same type of a reactive load with a distance delta L, again and so on in this way. So what I'm doing over here, I'm loading the transmission line periodically with period. Now what is the meaning of a period over here? Period is the separation between two successive reactive loads. So here the period is delta L, or we can call it as a separation. So what I'm doing over here, I'm taking initially a plain two-wire transmission line, and this transmission line I'm going to continuously load with a specific separating gap with the reactive loads. Okay, and this structure is going to primarily behave as a filter component. Okay, remember that this particular structure we call it as a periodic structure. So in general we call it this structure as a periodic structure. So remember that this periodic structure, basically when you analyze in terms of RF analysis, it will give you the behavior of pass band and stop band characteristics, right? So remember that the basic primitive or the backbone of the filter circuit is the periodic structure, and the periodic structure is a simple structure in which reactive elements are loaded periodically onto the structure with certain specific gap. And why this is done? This is done purposely in order to generate the effect of pass band and stop band characteristics. Okay, pass band and stop band characteristics. So the primitive structure which is utilized in the development of the filter circuit is the periodic structure, and this is one of the most commonly utilized periodic structure. When you load the transmission line periodically with a reactive loads, it will behave as a filter device. That means this particular transmission line now will no longer act as a transmission line, but it will exhibit certain transmission properties and certain stop band characteristics. So transmission and stop band, transmission and stop band. So this particular structure in general is going to exhibit pass band and stop band characteristic. And this is the basic principle of design of the filter. So this design of the filter, in any particular filter, if you see, the filter has to consist of a periodic structure, right? And this is what I explained you, what is the concept of periodic structure and how it resembles the stop band and the pass band characteristics, right? So the example that we took over here in order to illustrate the periodic structure is the transmission line which is periodically loaded with the reactive elements, right? So we go ahead with the next topic, terminated periodic structure. We will continue this topic. So we saw what do you mean by a periodic structure. Okay, so what if we terminate this periodic structure into specific load? Okay, let us say. So what I will do next, I'm going to take the help of the same diagram, right? So what I will do is now I will segment this periodically loaded transmission line into equal pieces in this way. Okay. Now this piece from this point to this point having the length of delta L, which is equal to the period of the transmission line. So this we call it the unit cell. Okay. Now what I will do is these unit cell I'm going to represent by using a two-port network. So what I will do now, so this unit cell over here, which is equal to the period of the transmission line, okay, which is acting as a filter. Now this unit cell, what I will do is I will convert this into a two-port network. So a two-port network will look like this. Okay, so it has a certain input, it has certain output. So this is the input port and this is the output port. Okay, so this we call it as a unit cell. So what I have done, I have taken some part of that segmented transmission line. I am representing that unit cell with a two-port network. So this is a two-port network presentation, right? So what we understood, we can take out some specific component of the transmission line and we can call it as a unit cell. Now let us go ahead and see what will happen when you terminate this unit cell, which is representing a part of the transmission line with a certain load. So we call this topic as terminated periodic structures. Terminated periodic structure. Okay, so let me draw it again. So what I will do, I will take this unit cell as it is. On the output port, I will terminate it with certain load. Okay, so how it look like then? So again, this is a unit cell representing the section of the transmission line, right? This is again an input port. This is output port. Now here at the output port, what I will do is I will terminate this output port with certain load ZL, right? This is a unit cell as it is. So what we have done over here at the output port, we have terminated the port with certain load impedance ZL. Okay. So let us say Vn is the voltage over here and In is the current flowing at the output port. Okay. So what we have done, we have taken a piece of that loaded transmission line, which we call it as a unit cell. And this unit cell we have terminated at the output port with certain load impedance ZL. Okay. And this particular structure is of very importance in order to understand the processing of passband and stopband characteristics exhibited by the filter structure. Okay. So this we call it as a terminated periodic structure. Okay. So why this is important? This is very much important in terms of understanding the concept of passband and stopband behavior. Now, how? Let us see. Okay. Let us say ZL is the load impedance. Okay. Say we are interested now in order to calculate the reflection that could take place at the output port. So here we are interested to calculate now reflection. Now first of all, why reflection will take place at output port? Why reflection is taking place now? The reflection is taking place because of termination of that output port. We already know that whenever the transmission line is short circuited, open circuited, or terminated into certain things, reflection will take place. Now we are interested in order to find out what is the reflection that would cause at the output port when it is inserted or it is terminated into a certain load impedance. Okay, so this insertion of load impedance at the output port will give rise to certain reflection coefficient. So let us say the impedance observed by looking inside the port number 2 is say represented as a Z. Okay, so Z is input impedance seen at port 2. Okay, and what is ZL? ZL is output impedance terminated. Output impedance terminated at port 2. Okay, so we know what is the input impedance that we can get by looking into the port number 2 of this unit cell, which is represented as a 2-port network. And we know that this output port is terminated into the load impedance ZL. Okay, so how to calculate the reflection coefficient? Then reflection coefficient is given by, what is that formula of reflection coefficient? Reflection coefficient gamma, how it is given? It is given as gamma is equal to ZL minus Z upon ZL plus Z. So this is a simple way to calculate the reflection that could take place at the output terminated port of this unit cell. Okay. Now remember over here that if the condition, if the load impedance ZL becomes equal to Z, what will happen? When this happens, then the reflection comes out to be zero. When the reflection comes out to be zero, what that indicates that all of the signal you are supplying at the input port, all that signal will reach at ZL, because at ZL there will not be any reflection, provided if ZL value, if we manage it to keep to the input impedance seen by looking at port number 2. Okay, so anyhow, if we are able to do this, that is keeping ZL is equal to Z, then the reflection coefficient becomes 0. And what that indicates that whatever input signal that we pass on, all of the input signal will get absorbed by the ZL and nothing is getting reflected back. Okay, so how this can be represented in terms of a waveguide then? Now in terms of a waveguide, we already know the propagation constant, okay, the wave number, the cutoff frequency wave number, right? So let us apply the same concept to these parameters of the waveguide. Okay, so beta here we represent as propagation constant. Let us say beta is a propagation constant. K is free space wave number. Okay, I hope these terminologies of the waveguides are known to you since from our last semester microwave engineering subject whenever we studied the waveguide chapter. Okay, and similarly Kc is the cutoff wave number. Cutoff wave number. So how we can establish a relationship between these three parameters of the waveguide? So these are the parameters of the waveguide. Parameters of waveguide. Okay, so how we can establish a relationship between these parameters? So the relation that we already know, that propagation constant beta is equal to square root of k square minus kc square. So this is a relationship between propagation constant, free space wave number, that is k, and cutoff wave number, that is kc. Okay, or in other words, the same equation, this can be rearranged, and how it is can be written: k is equal to square root of beta square plus kc square. Okay, so this is in terms of wave number, and this is from the waveguide theory that we know. Okay, so what is Kc? Kc is the cutoff wave number, K is the free space propagation wave number, and beta is the propagation constant. Okay, now here there is one very important observation as far as waveguide we want to utilize as a filter device. Okay, see here, if the condition, if K is less than Kc, what will happen? In this particular equation, we know the equation of the propagation constant beta, which is written in terms of k and kc. Now, if the value of the k is less than kc, what will happen? The beta here will become imaginary, right? So, what is the meaning when the propagation constant becomes imaginary? So the meaning is when the beta becomes imaginary. When will it will become imaginary? When the value of the k becomes lesser than kc. At that time, the value of the beta will be imaginary. And what is beta? Beta is representing the propagation constant. And that means the propagation constant becomes imaginary. So this indicates what? Propagation is imaginary. Propagation of what? Propagation of the signal is imaginary. So propagation of the signal is imaginary means there is a no propagation action taking place. It is a simple meaning. So what is this meaning? Propagation is imaginary means no propagation. So whenever we came to the term imaginary propagation, that indicates that there is no absolutely propagation of the signal is taking place. So what this indicates then? No propagation means this is a stop band behavior, right? So this we can call it as a stop band behavior. That means the signal is not propagating, the signal is stopped, and we call this as a stop band behavior. Okay. So what will happen when we maintain the value of k such that it is lesser than cutoff wave number, that is kc? At that time, the propagation constant will become imaginary, and that indicates that propagation is imaginary. That means there is no propagation at all, and whenever there is no propagation, the signal will not propagate, and it simply indicates that it will show us the stop band behavior. Okay. On the other hand, if k is greater than kc, okay, so in that particular case, what will happen to the propagation constant beta then? Now, in this particular case, the value of beta becomes real value. Okay. So, whenever the value of propagation constant is a real, it indicates true propagation of the signal. True propagation of the signal. Okay. So, true propagation of the signal means the propagation will actually take place of the signal, and this in turn will indicate pass band behavior. Pass band behavior. Okay. So you understood how we correlated the parameters of the waveguide in order to explain the process of stop band and pass band characteristics. Okay. So here the second condition, whenever the free space wave number is greater than the cutoff frequency wave number, at that time the propagation constant beta will become a real value, and whenever it becomes a real value, it indicates that propagation will take place, and it shows the behavior of passing of the signal. Okay. So this all we discussed about the waveguide. Okay. And that means we can make use of the waveguide in order to design the filter circuit, because we just right now explained how by taking the parameters of the waveguide, we can develop the passband and stop band characteristics. Okay, so this is very important concept over here, how the waveguides can be utilized as the filter circuit. Okay, so whenever the k is lesser than kc, it will give us the stop band characteristic, and whenever the value of k is greater than kc, then the propagation constant will become a real, and it will provide us the passband response or passband behavior. Okay. So from here, the only intention was to tell you that the waveguide can be utilized as a filter by controlling the waveguide parameters in terms of wave number. Okay. So we go further about this filter circuits. Now next what we are going to discuss is the filter types. Already we discussed the filter types. Okay. So filter types, we already shown you the primitive types based on the frequency response, which is plotted with respect to insertion loss and frequency. So the main configuration of the filter, we can classify them based on the frequency response: low pass filter, high pass filter, band pass filter, and band stop filter. Okay. And typically the microwave or RF frequency filters that we are going to design, they typically have the frequency range starting from say 100 megahertz, 100 megahertz to 300 megahertz and up to few gigahertz also. Okay, so this is a typical range of the filter circuit for which we can design the RF and microwave filters, right? So 100 to 300 megahertz is a typical frequency response, and we can go up to few gigahertz level also, right? So in terms of the circuit design, the filter can be constructed in a two different ways. Okay, in terms of circuit configuration, filter classification, I will call it as a filter classification. With respect to component type, with respect to component type. So how we classify the filter based on the type of a component which it makes utilization of. So this can be classified into two types: passive filters and active filters. So what is passive filters? The filters which makes use of inductors, capacitors, resistors for their construction as the passive element. So when we make use of these components in the design of the filter, we call it as a passive filter, because inductor, capacitor and resistors, these are the passive components. Okay. On the other hand, we can also design active filters. Now for active filters, the filter should make use of certain active element. So the active element like transistors, diode, op amp. Okay. So if your filter circuit is going to make use of any of these components like transistor, diode, operational amplifier, then these types of filter we call it as an active filter. Now definitely here when we design the active filter, they are going to provide us the another benefit that along with the filter operation we can accomplish some other operations like amplification of the signal itself. Okay. On the other side, the passive filters are not capable of providing us the extra functionality. Okay, because the passive filters are only supposed to provide the basic filtering mechanism and nothing else. Okay. On the other hand, if we make use of devices like transistor, diode, or operational amplifiers in the design of filter circuit, along with the filtering operation, they can provide us much more other functionalities like amplification operation. Okay, so based on active and passive filters, the filters can be classified into two categories. Okay, so in our particular syllabus, we will be more focusing on construction and design of passive filters. Okay, and as I already said in the beginning of this lecture, so there are two specific ways of designing that particular filter, so that we are going to see within no time. First method is the insertion loss technique of designing of filter, and second method is image parameter method. So these are the two basic methods with which the filter can be designed. Okay, and the details of these methods we are going to investigate in our further lectures. Okay, remember that we are not going to involve in the design of active filter, but we will be focusing and restricting ourselves to the design of passive filters only, right? So if you have any particular doubts up to this discussion, you can ask. Otherwise, we will go ahead. Yes, student. You have any particular doubts? Yes, may I know? My voice is audible to you, all of you, right? So let us go ahead and discuss the next part, that is parameters of the filter now. Let us discuss parameters of filter, or simply we can say filter parameters. What are filter parameters? Okay, so filter parameters are the parameters which are utilized in order to design the filter itself. Okay, so there are certain important parameters with which the specified filter can be designed. Okay, so suppose if I say design a filter. Now, in order to design a filter, you need to specify certain parameters. Okay, so these parameters are typically given by the user for which we are going to design a particular filter circuit. Okay, so the parameters with which the behavior of the filtering process or the filtering operation is specified are known as a filter parameters. Okay, suppose I want to design a filter which only passes a frequency from DC to say 2 megahertz. Okay, so this is what we call it as a specification of the filter. So filter parameters, or we call it as a specification parameters of the filter. Specification parameters of filter for which the filter is designed. Okay, so what are the in general or commonly utilized conventionally specifications of the filter? Okay, so the first filter parameter with which the specifications are given are pass bandwidth, pass band, pass band width, you can say, or you can simply call it as a, or you can say it is a pass band. How much pass band should be there? So that is the single first important parameter. Then we have another parameter called as a stop band attenuation. How much should be the attenuation in the stop band of the filter? So this is another important parameter in the design application. Third, obviously, the frequency range. It has to be there. Otherwise, we cannot design a filter. Frequency range, or we can call it the ranges also, if we involve more than one frequency. Then another filter parameter important in the design consideration is required input output impedances. Required input and output impedances. Okay, so this is also one of the important required parameter. The next is how much should be the return loss. So we'll come to these definitions in more detail later on. Return loss has to be specified. Very important. Next is the insertion loss. See, there is a whole one single unique technique of insertion loss with which the filter can be easily designed. Okay, insertion loss. So we'll come to this definition later on. And then another parameter is we call it as a group delay. Okay, so one by one, let us go into the details of this filter parameter, and we will see what is the significance of these filter parameters, right? So pass bandwidth or the pass band, what it indicates? It can be represented conveniently by looking at a particular diagram. Okay, so here I will draw the simple diagram again here. Again, I will draw the same diagram, right? Insertion loss versus frequency in this way. Okay, so let us say the low pass frequency response in this way. Okay, so from 0 to certain frequency fc, we have minimum insertion loss, so that means this is a pass band, and from fc onwards to f infinity we have a stop band. Okay, so the first definition of the pass band. So what is the pass band going to indicate? The pass band is going to indicate the bandwidth for which the filter is supposed to pass the frequency component. Now, right now, this width is 0 to fc. So that is the meaning of the pass band or the pass band width. Okay, so the pass band width, it indicates that from which frequency the filter should start passing the frequency and up to what frequency range, 0 to fc. Then stop band attenuation. See here, the attenuation will take place when the insertion loss becomes high. Okay, so here there has to be certain finite value of insertion loss value x. Okay, so stop band is typically exhibited in this particular range. Okay, so this is a stop band which I am showing with a hatching pattern. Okay, so in the stop band, a typical value of insertion loss can provide us how much the signal is getting attenuated. Ideally, in the stop band, the attenuation should be infinite, right? It should be as high as possible, and the insertion loss is going to be high. So the frequency range or the pass band, these two definitions are utilized more or less simultaneously. So the frequency range is nothing but the pass band. Okay. So the required input and output impedances. So this particular point number 4, required input and output impedances. So we already saw that the filter is represented by a two-port network, right? And this filter is utilized to filter out certain things. So it has to be connected at certain source at port number 1, and this has to be connected at the output, or you can call it as a load, output load at port number 2. So what we are actually doing, we are inserting this two-port network which is representing a filter circuit in between source and in between load. So that means we are actually inserting a filter device in between source and load in order to filter out some of the components from the source and in order to provide that to the load. Okay, so this itself indicates certain return loss and insertion loss concept. Okay, so let us say the source is providing input power to the load via the filter. Now this input power is pi. Okay, so out of this input power, some of the power will get passed through the filter and some of the power will get reflected back. So the reflected power which gets reflected back from the input of filter, I will label it as a PR. Okay, so PR is the reflected power right at the beginning of the filter. Okay, so the actual amount of power that will get delivered to the load will be then Pi minus PR. Okay, so the reflected power, you need to subtract it from the input power, so that amount of power will get delivered to the output load. Okay, and the final power given to the load is denoted by PL. Now from these different definitions of power, now I will elaborate the equation or the calculation of insertion loss and return loss. Okay, so how the insertion loss is given then? Now the definition of insertion loss. Insertion loss, or in simple way we call it as a IL. It is expressed in a dB, decibel scale. How it is given? It is simply given as the ratio of the power at the input to at the output. So at the input, what is the power? At the input, we have the power Pi, and at the output, we have the delivered power PL. So how the same can be written in terms of reflected power and intermediate power? So this can be written as 10 log to the base 10. Input power we keep as it is Pi, now divided by PL. Now what is PL? PL is nothing but Pi minus PR. This you can write. Okay. So if we take Pi from the numerator, divide numerator and denominator by Pi. When I divide numerator, I will get 1, right? So here what I will get, Pi upon Pi, I will get 1 minus Pr upon Pi. Okay. So I will write over here further. So insertion loss in dB, how it is represented then? 10 log to the base 10 of into whole bracket 1 divided by 1 minus Pr upon Pi. Now what is Pr upon Pi? It is a ratio of power. What is PR? PR is the reflected power. What is PI? PI is the input power. Now the same can be represented in terms of voltages, and this can be conveniently represented as a reflection coefficient. So 10 log to the base 10 of, so the same can be written as 1 upon 1 minus mod gamma square, where gamma is the ratio, gamma square rather is the ratio of PR upon PI. So this is very important. So the insertion loss is always defined as the loss that the filter circuit is going to accomplish when it gets inserted in between source and load. Okay. Remember, insertion loss is a very important parameter, and insertion loss can be calculated once we know the reflection coefficient. Okay. Going further to the next definition of return loss. Okay. So how the return loss is given then? Return loss, or we simply call it as a RL. RL in decibel. Again, it is represented in terms of a decibel unit. Okay. So how it is given? Return loss is simply given by the again ratio of power 10 log to the base 10 of, right? So again I will come back over here, 10 log to the base 10 of, it is a ratio of Pi upon PR. Okay. So reflection loss is the loss that is taking place because of the reflection of the inserted device. The inserted device is a two-port network, is a filter in between source and load. And whatever reflection that is taking place at the input port, so that reflection power, we are taking it as a PR. Okay. And if I divide the numerator and denominator by Pi, the same can be written as 10 log to the base 10. Now divide the numerator and denominator by Pi. I will get 1 in the numerator, and in the denominator I will get PR upon Pi. Okay. But what is PR upon Pi? From the earlier equation, we know this is equal to gamma square. So this can be written as 10 log to the base 10 into bracket 1 upon mod of gamma square. Okay. So there is a difference between the return loss and the insertion loss. Okay. So the return loss is related with the reflection coefficient, and the insertion loss is going to deal with the amount of power that will get lost due to the insertion of the filter device or any other device in between source and load circuit. Okay. So I hope you understood the definition of insertion loss and return loss. Okay. Next, coming to the filter parameter, that is a group delay. Okay. So what is the significance of a return loss? Return loss, it quantifies the amount of impedance matching. So whenever we are going to deal with the impedance matching properties, return loss is going to play a very important role. Okay. Now the next parameter of the filter specification is the group delay. Okay. Now what is the group delay here? Now group delay of the filter is another important specification of the filter during the design consideration. The group delay is important for multi-frequency or pulsed signal in order to determine the frequency dispersion or the frequency deviation from the constant group delay over the given frequency band. Okay. So group delay of the filter is given by equation TD. TD is nothing but a group delay. How it is given, how it is calculated? It is calculated 1 upon 2 pi multiplied by d phi of t divided by df. Okay, so what is phi term over here? Phi term, it indicates the transmission phase. Okay, and df stands for the frequency range. Okay, so here what is the meaning of a group delay? Group delay is resembled as the frequency dispersion or the frequency deviation property from the constant group of the frequency component from the given frequency band. Okay, so sometimes in the design of filter, group delay is going to be specified, and it is calculated by using this particular formula 1 upon 2 pi d phi of t upon df, where phi of t, it is a time dependent phenomena, and it indicates phi is nothing but the delay in the propagation with respect to certain group of frequency component. We call it as a frequency deviation df, right? So these are the important specification parameters of the filter, which the user always supposed to specify as on when it is required to design a filter circuit. So out of which the frequency range, the passband and stop band attenuation, the required input and output impedances, return loss and insertion loss, these are the main and important filter parameters for the design purpose. Okay, so I hope you understood what are the different filter design parameters and what is their significance and their definitions. So up to this particular point, if you have any particular doubt, you can ask me, or otherwise we will go ahead. Now let us discuss now with the methods of filter design. Methods of filter design. Okay. So as I already told you in brief, there are two unique methods of designing the microwave or RF filter. The first method is a straightforward, which makes use of image impedances. Okay, so that we are going to see in a detail when we start image impedance design. So first, let us discuss now filter design methods. I will give the heading as filter design methods. Yes, students, if you have any doubts, you can ask. See, this entire lecture is getting recorded. You will be given a copy. Direct a copy will be saved in the MS Team. You can go later on there and you can download the same video lecture and you can watch it later also if you want. Okay. So filter design methods. So there are two methods of designing the filter. The first method is image parameter method. Right? Image parameter method. And the second method of filter design is insertion loss method. Insertion loss method. Say in our syllabus, we are going to design the RF or the microwave filter by using both of these techniques. And we will also investigate how these two filter design techniques are different from each other. Okay. So let us go one by one. What is the meaning of image parameter technique and what is the meaning of insertion loss technique, right? Now, filters are designed using image parameter technique will consist of cascade of two simple port filters. Okay, so whenever we design a filter using image parameter, it consists of cascade of two port networks. Okay, now these two port network, these two port networks can provide us can provide us stop band and passband characteristics. And this is how this image parameter is going to work. Okay. See, what is the basic principle of image parameter method? Image parameter method of filter synthesis. So sometimes these methods are also called as a synthesis methods, remember. So it is one and the same, synthesis method of filter or filter design methods. So one and the same. So synthesis method of filters or the filter design method, one and the same. So first method, image parameter method. What it consists of? In this particular method, we are going to make use of cascading of two-port networks. Okay, and these two-port networks are analyzed in terms of transmission parameters. Okay, so here I will write two-port networks are represented by transmission parameters. Okay, and these transmission parameters are ultimately represented as a impedances. So transmission parameters, see how the sequence of designing I will explain you. First let me write the things. Transmission parameters are expressed as image impedances. We'll come to this point later on. Okay, so what is the terminology of designing a filter using image parameter technique? So basically in image parameter technique or synthesis of the filter, we are going to make use of cascade of the two-port networks. Okay, we already know that a two-port network can be represented as a unit cell. Okay, and we saw that it can be replaced with a waveguide which can exhibit passband and stopband characteristics. So these two-port networks are represented as a transmission line parameters, or they are also known as ABCD parameters. And what we are doing, we are expressing the ABCD parameters of the two-port network in terms of image impedances of the given network. And that's why this method is named as image parameter technique. Okay. See here, two port networks are utilized. So these two port networks are selected based on the desired cutoff frequency and the attenuation characteristic, which will provide a particular frequency response over the complete range of operation. Therefore, the procedure of the filter design using image parameter is very and relatively simple and straightforward. Okay. See, the image parameter method is a very simple and straightforward technique in order to design the filter. And it determines what properties of passband and stopbands are required by calculating the properties of infinite chain sections which are represented as a two-port network, right? So the image impedance of the two-port network is going to play a very important role in the design consideration. Okay, so what is the image impedance? The image impedance is defined as the impedance of infinite chain of identical transmission line sections. Okay, so here I will elaborate. Let us say this is a transmission line. This transmission line, okay, is divided into sections, right? And in these sections, we are adding reactive load. Okay, so this is what we call this transmission line is now loaded with reactive loads. Okay, And this will become a periodic structure again because these loads we are going to repeat it throughout the length of a transmission line. And what we are doing is we are going to pick up this particular section. Okay, and this particular section we are representing as a two-port network. Okay, and this two-port network is represented, so this is a two-port network, this section, and this two-port network is represented in terms of ABCD transmission parameters. And we will see later on that these ABCD parameters are expressed in terms of image impedances, which the two-port network is going to terminate with. So Zi2, and say here at the input we have another impedance Zi1. So what we are doing basically, we are taking the transmission line, dividing the transmission line piecewise. We call them as a unit cell after loading with reactive element, right? In order to exhibit passband and stopband characteristic. We are taking the piece of that particular transmission line and we are converting that into a two-port network. This two-port network is then now represented in terms of transmission parameters ABCD, which are specified in terms of input and output impedance Zi1 and Zi2. And that's why the overall design of the image parameter method will take into account the impedances, those are terminating at the input and output of that two-port section representing the part of the transmission line, right? So the image impedance is defined as the impedance of finite chain of identical section of transmission line section. So these basic sections are connected to a ladder network of several sections. The number of sections required in order to construct a particular filter is mostly determined by the amount of stop band rejection required. The image analysis starts with a calculation of input and output impedances. So these input and output impedances I have shown over here as a Zi2 and Zi1. So these impedances are called as image impedances. And then transfer function of this section of this infinite chain of identical section is evaluated. Okay. So image parameter method, therefore, it relies on each filter section because we are going to represent each section of this unit cell of a transmission line as a unique filter. So therefore, the design of filter using this synthesis method, it relies on performance of each filter section or each component. So these filters are usually terminated with a fixed resistance and they will they cannot match perfectly at one particular specific frequency. Okay, so this we can call it as a drawback of image parameter technique because image parameter method cannot be utilized to perfectly match at a particular specific frequency, and therefore there has to be always a mismatch, and because of this mismatch in the design of image parameter synthesis method, reflection will take place, right? And whenever reflection will take place, the cutoff frequency we will not get a sharp cutoff response, but on the other hand we will get a gradual response, right? So in the case of image parameter method, the basic building block of the filter that we will see later on is the constant K section filter. So here I will write constant K section filter. Okay, so these are the basic building blocks of filter design using image parameter method. So always remember that we are going to start with constant K section. So these are the basic building blocks of designing an entire filter using image parameter technique. Okay. So let us see now in brief what is the another technique, that is the insertion loss technique. So what is the insertion loss technique then? The insertion loss technique is a bit more sophisticated way of designing the filter as compared to image parameter. Okay. So network synthesis method is used to design the filter. Okay. So here what type of procedure we are going to make? Network synthesis we are going to make use of. Network synthesis is used for the design of entire specified frequency response. Okay, so what we do in this particular synthesis method, first we design low pass filter prototype. First we design a low pass filter from the given specification. Okay, and once this low pass filter is designed, we perform normalization operation. We'll come to this procedure later on, but for time being, you just understand we perform normalization of impedance and frequency scaling. We perform. See, we do a frequency scaling in order to transform the filter from low pass primitive type to any other type. Okay. So what is the procedure of designing a filter using an insertion loss method? Network synthesis method is used in order to express the specified insertion loss into the design aspect. So what we do is, basically in the insertion loss technique of filter synthesis, we always start with designing low pass prototype. After designing a low pass prototype filter, we will transform that filter into the desired filter response. It could be either high pass response, band stop response, or band pass response. And then we will normalize or scale the impedance and frequency as per the desired frequency response. Okay. So a common thing between image parameter method and insertion loss method of filter synthesis is that both these filter are going to be designed by making use of passive elements, that is we can make use of lumped elements, inductors and capacitors. So that is a commonality between image parameter method and insertion loss method, right? So inductors and capacitors we are going to make use in both methods, in image parameter as well as in insertion loss technique. But remember that insertion loss technique of filter synthesis is much more sophisticated when it is compared to image parameter method. The drawback of image parameter method is that the frequency response reshaping cannot be done as per the desired expectancy. But in the case when we design a filter with insertion loss technique, the same can be done. So that's why insertion loss method is said to be a sophisticated technique when it is compared with image parameter technique, right? So I hope you understood the basic two different types of filter design methods or procedures, or we would also call it as a synthesis techniques. So let us go ahead and see the next topic after the filter synthesis technique, that is image parameter technique. Okay. Now image parameter technique we are going to start with now. So up to this particular point, if you people have any particular doubts, you are free to ask, because later on we will be going with the details of an image parameter based technique of filter design, and for that initial understanding of all these concepts is very much necessary. So up to this particular point, students, if you have any particular doubts, you can ask. Yes, I will take a break of a couple of minutes. Meanwhile, you just go through whatever points that we have discussed in these 2 hours. And if you have any particular doubt in understanding any particular concept or missed out anything, you can ask. And after that, we will start with the first method of filter synthesis, that is image parameter technique. So take your time, a couple of minutes, and then we will be again starting. Yes, students, you have any particular doubts? Meanwhile, you can ask or you can discuss the thing. Yes, Soham is there.
Yes, I'm there.
Okay, so whatever these notes that I will be making for every lecture, so these recordings will be available. Okay, so as on when we finish the session, these recordings will be saved automatically to the Microsoft Stream. From there, you can download it. See, we are just forming the basic foundation of filter design, but we haven't started yet with the design. Okay, but we are starting with theoretical understanding of the filter concept. Later on, we will be spending our much time into the designing aspect. That will take time. But before that, you should know the basic concept. What is image parameter technique? What is insertion loss technique? And how they are different? And how exactly the filters are going to be different when they are going to be designed with these methods. You just tell me whether the handwriting, the voice, everything is visible to you whenever I'm performing over here on my tablet. Yes, Soham.
Yes, sir, it is visible.
Handwriting, is it visible?
Yes, sir, yes, sir.
And what about voice?
Yes, sir, you're audible.
Okay. So I see here there are around 8 to 9 people. Where are the other people? They have gone somewhere or for a picnic or what? During the time of induction or orientation, the strength was very poor. There were about 30 to 35 students were present during that day of presentation during the induction program. Okay, you just pass on the message because we already started with our curriculum from the last Monday. Okay, and this time also we'll be totally delivering you people the teaching mechanism through the online mode only. Okay, so the things will be similar to that of whatever we have conducted last time. So the submission, the practical experimentation, everything will be evaluated online. Okay, let us go ahead with image parameter technique. So we are going into the details of foundation of this technique. Let us start with. So let us start with image parameter technique. So you just pay attention. What is the basic of this image parameter technique? So what is this image parameter technique? This is one of the technique of designing a filter. So I will give the heading as image parameter filter design. So how exactly we are going to design a filter by using this method? Okay. Now for that, you just recall this above diagram. So this diagram is available over here. So a transmission line, we have loaded that transmission line with reactive elements periodically. And a piece of that transmission line, we are considering it as a two-port network. Okay, so let us redraw the same structure again. So a piece of this that transmission line, we call it as a two-port network. So let us say this is a two-port network representing a section or a piece of that transmission line. So this is a two-port network. Okay. Now this two-port network, you know the different parameters. You know the scattering parameters. You know the chain parameters. You know the ABCD parameters. Okay. We are analyzing this two-port network in terms of ABCD parameters. Okay. So what are ABCD parameters? ABCD parameters are transmission parameters in which the voltage and current at a given port are expressed in terms of voltage and current at some other port. Okay, so how many ports we have over here? Here we have two ports Okay, so this is port number 1 at the input, port 1, and this is port number 2 at the output. Okay, now let us say at port number 1 we have inserted or we have connected certain impedance. Now this impedance we call it as a ZI1. We call it as a image impedance ZI1. Similarly, at the output of this two-port network, we have connected another load impedance. Now this load impedance, let us call it as a ZI2. Okay. So what is ZI1? ZI1 is the image impedance, right, at port 1. Okay. And what is ZI2? ZI2 is the image impedance again at port number 2, right? So this is very quite clear that we are representing a piece of that transmission section with a two-port network. Now this two-port network we want to represent in terms of ABCD parameters. We call it as a transmission parameters, right? And at the input and output of this two-port network, we are connecting image impedances ZI1 and ZI2. Okay. Now let us say Zin is the impedance obtained by looking at the input of two-port network Zin. Okay, and let us say Zo is the output impedance looking from the output side of this two-port network from the port 2. So what is Zin? Zin is impedance obtained by looking at port 1 of two-port network. And similarly, ZO, what is ZO? ZO is again the impedance obtained by looking at port 2 of the two-port network. Okay, so let us say at the input we have voltage V1, so voltage V1 and current I1, voltage V1 and current I1. And similarly at the output port, let us say we have the voltage V2 and current I2. Okay, so we have the four parameters over here, two voltages and two currents, voltages V1 and V2 and current I1 and I2. Now you already know how the transmission line parameters are expressed. These are expressed as voltage and current at one port with respect to voltage and current at the other port. So here we have a two ports, port 1 and port 2. We have V1 as a voltage at port 1, I1 as a current at port 1. Similarly, we have V2 as a voltage at port 2 and current I2 as a current at port number 2. Okay, so ZI1 and ZI2, these are representing the image impedance of the filter. Okay, so with already known theory by ABCD parameters, so if we want to relate V1 I1 and V2 I2 by using transmission line parameters, so how we can express those? So we can write voltage V1 and current I1 in terms of voltage V2 and current I2 as AV2 plus BI2, right? Let us call this an equation number 1. And similarly, the current at port number 1, I1, is represented as CV2 plus DI2, right? So how we can write this equation? We wrote this equation by taking into account ABCD parameters, transmission line parameters. Okay. And how we can express the input impedance Z in? Z in is nothing but ratio of V1 divided by I1. So if we substitute the values of V1 and I1 from equation number 1 and 2, how we can write this? AV2 plus BI2, right, divided by CV2 plus DI2 by simply substituting the equation values of V1 and V2. Okay, so what I will do now is I will take I2 from the numerator and denominator. Okay, so see how I can write. So I will write this the A V2 by I2, right? I will divide the numerator and denominator by I2, right? So I will get this term, and in the denominator C into bracket, what I will get? V2 divided by I2, because I'm taking common I2, right? Plus D. Okay. So what is V2 to I2? The ratio of V2 to I2 will provide us ZI2. Okay. So here I will write, but V2 divided by I2 is nothing but ZI2. So how we can write this then? Z in, this can be written as A. Now I will replace this V2 by I2, this particular term, with ZI2, right, plus B divided by C ZI2 plus D. Okay, let us call this as an equation number 3. Okay, say this two-port network is going to follow the reciprocity condition. Okay, so reciprocity condition means input port and output port, they can interchange their position. That means input port can become output and output port also can become input port. If it's the case, then we can satisfy a condition, that is AD minus BC is equal to 1. Okay, so this condition holds true when this two-port network is supposed to follow the condition of reciprocity. So based on this, similarly, we can write down the equations of voltage and current at port number 2, which are expressed in terms of voltage and current at port number 1. So on the similar basis, we can write here V2, how we can write? By taking into account the property of reciprocity, we can write dV1 minus BI1 in terms of voltage and current at port number 1. Let us call this an equation number 4. And similarly, I2 is given by minus of CV1 plus AI1. Let's call this an equation number 5. Okay, and if I take the ratio of V2 to I2, V2 to I2 will give this the output impedance ZO. See here in this particular image, see this ZO. ZO can be given as a ratio of V2 divided by I2, right? So V2 divided by I2. So if I take the ratio minus of, okay, because it is a reciprocal. So minus of V2 is dV1 minus BI1 divided by I2 is minus CV1 plus AI1. Okay, so if I take I1 term as a common term, okay, so dV1 upon I1. If I take I1 as a common term in the numerator and denominator, I will be left with this equation in the numerator divided by now CV1 upon I1 plus A. Okay. So how this can be written? Now what is V1 divided by I1? Now V1 divided by I1 is nothing but ZI1. That is the image impedance. So this can be written as ZO is equal to what we can write then? Finally, D, right? ZI1 plus B by changing the sign, and in the denominator CZI1 plus A. Let us call this an equation number 6. Okay. And what is ZI1 actually? ZI1 is actually negative ratio of V1 upon I1. Let's call this an equation number 7. Okay. But we know that what we know, but we know that Zin Zin is the input impedance. Okay, so Zin is nothing but Zi1, image impedance 1, and similarly Zo is nothing but Zi2. Okay, therefore from equation 3, from equation 3 and 6. Okay, so from equation 3 and 6, what we can write? We can write in this way directly, rearranging the terms Zi1 C into Zi2 plus D equating A into Zi2 plus B. Call this an equation number 8. And similarly from equation 6, comparing, what we can write, Zi2 into bracket CZI1 plus A is equal to D into Zi1 plus B. Call this an equation number 9. Okay. So what we do is, now we subtract equation 9 from equation 8 and we simplify further. Now what we do is subtracting equation 9 from equation 8 and simplifying. So what we get then? Say when we do this, what we get is, we will get finally image impedance 1 is equal to square root of A into B divided by C into D. Let us call this an equation number 10. And similarly, the image impedance at port number 2, that I will get Zi2 is equal to square root of B into D divided by A into C. Equation number 11. Okay, so what we observe? Equation 10 and equation 11. These are the two important equations. So what we observe from these two equations, equation number 10 and equation number 11, we observe that the image impedance of the two-port network, they are represented in terms of transmission parameters of the two-port network, right? So what are the transmission parameters of the two-port network? These are A, B, C, and D. So we have successfully managed to represent the image impedance of the two-port network in terms of its transmission parameters. Okay. So how the transfer characteristics is given then? The transfer characteristics and the propagation constant is given by, say, the propagation constant e raised to minus gamma, where gamma we call it as a propagation constant, and negative symbol, it represents that it is a forward traveling wave. Okay, so how it is given? It is given by square root of AD minus square root of BC. Let us call this an equation number 12. Okay, we know if it supports reciprocity, or reciprocity, if the two-port network is reciprocal, we already told what is reciprocity. Input can be exchanged with the output and vice versa. Then AD minus BC is equal to 1. Therefore, cosine hyperbolic function of that propagation constant gamma is given by in terms of square root of AD. Let us call this an equation number 13. Okay. So here, what is gamma? Gamma is nothing but propagation constant. Propagation constant. So what we see finally by equation number 13? Equation number 13 tells that the gamma term of this two-port network. So what the gamma is indicating? The gamma is indicating the propagation constant. Propagation constant of what? The propagation constant of the signal. The propagation constant of the signal is related with direct transmission parameters of the two-port network, that is square root of A into D. Okay. So here we have formed successfully the foundation of how the image impedances are related with the transmission parameters of the two-port network, as well as we saw that the propagation behavior of the stop band and passband characteristic is conveniently represented in terms of these transmission parameters itself, right? So in the image parameter synthesis technique, the image impedances Zi1 and Zi2, they are represented in terms of transmission line parameters of the two-port network, as well as the propagation behavior. The real part of the propagation behavior is expressed in terms of again transmission parameters, which is given as product of square root of A into D. Okay. So the basic building blocks which are utilized for designing the filter using image parameter method makes use of T and pi networks. Okay, T and pi networks. So what are these T and pi networks? T network is a network which resembles a T-like structure having certain reactive elements in its arms. So this is a typical T network. Okay. And alternative to this is a pi network where the first element is a parallel element, second element is series, and again the third element is parallel. Okay. So all these reactive elements which are present in the arms are having certain impedances Z1, Z2 and Z3. So the first element over here in the case of T configuration is series, parallel, and second element is parallel, and third element is again series. In the case of a pi network, it looks like a pi type of a network. So these are the basic building blocks of filter design using image parameter technique, in which we will take into account the impedances. So Z1, this is Z2, and this is Z3. And the first element in the case of pi network is a parallel element. Second element is a series, and third element is again parallel. So one can choose any of these basic building sections in order to construct the filter using image parameter technique. Okay. So either we can make use of this T network or pi network as a basic building block of filter design using image parameter technique. Okay. So I hope you understood how the image parameter technique look likes and how it is exactly being utilized for the design of filter. So what actually it happens in the image parameter method is that the piece of the transmission line is represented in terms of two-port network, and this two-port network is represented in terms of transmission line parameters, ABCD parameters, which are then related with the image impedance of the two-port network, Z in 1 and Z in 2. And based on that, we are going to make use of T network and pi network configuration as a basic building block of the filter circuit. Okay. So I hope you understood the basic concept of how exactly we are going to make use of image parameter technique for the filter design. Okay, so we go further now. So the two-port network, I will skip the next part. So the next part is actually that is the definition of two-port network, then the different types of parameters associated with a two-port network. We already know that low frequency analysis is easily accomplished by using Z parameter and Y parameter. Okay, and why scattering parameters are important and ABCD parameters are important. Okay, so the importance of the ABCD parameters is that whenever we make use of ABCD parameters in the design of filter, which makes use of image parameter synthesis technique, is that they are going to facilitate us the cascade of the multiple two-port networks together. So here, why we are using the transmission line parameters or ABCD parameter, and why not scattering parameters? The reason is that the two-port network that we are going to make use of as a basic building block in the design of a filter is conveniently expressed whenever it needs to be cascaded. See, remember, actual filter is not a single two-port network. Let us say this is a two-port network number one. It is connected with another two-port network. Let us say this is network number two. Again, it is connected with another network. This is network number three. Okay. And then this entire structure. Okay. So what we call this as the cascade of two-port networks. This we call it as a cascade of two-port network. And then here we are terminating with image impedances Zi1 and Zi2 and Zi1. Okay, so whenever we want to combine these networks with each other in the cascaded configuration, ABCD parameters are most conveniently and commonly used, and that's why we have analyzed the image impedances Zi1 and Zi2 in terms of ABCD transmission parameters. Okay, and this Zi1 and Zi2 is constructed either using a T network or the pi network based on how many sections that we are actually going to need for the construction of filter. Okay, so this is why we are using the transmission line parameters. Okay, so at microwave frequencies, physical length of the component or the transmission line becomes comparable, or it could become much larger than the single conductor wavelength. Therefore, further for the measurement of impedance, admittance, ABCD parameter is very difficult to use. Okay, and we just saw why we are going to make use of transmission parameters, because we need a filter which is to be designed in terms of cascade of multiple networks. So that's why we need ABCD parameters. Okay, so I hope you understood the basic foundation of filter design using image parameter technique. Okay, so once we start with typical design of the filter that we normally call it as a basic building block as a constant K section filter under the image analysis technique, it will be clear to you how to actually implement and design the filter using this technique. Okay, so still some time is there. We will take one more article. Network presentation with ABCD parameter. Let us revise this. Okay. Network representation using ABCD parameters. As I already said, this is just the revision of ABCD parameters. How to represent a two-port network in terms of ABCD parameters. So that briefly we will discuss now. Network representation in ABCD parameters. So let us discuss this because we are dealing with ABCD parameters. Okay, let us say this is a two-port network, right? Two-port network, right? This has the input port. Okay, let's call this as the input port, and this is the output port. Okay, let us say we have supplied certain voltage at the input port, so we'll get certain current I1. And similarly, at the output port, we will develop certain output voltage. Let us represent that as a V2, and we will get a current, say I2. Okay. So what is ABCD parameters? ABCD parameters will let us to express voltage and current at one port with respect to voltage and current at other port. So if we take use of ABCD parameters, how we can express the voltage V1? Voltage V1 is given as A times voltage at port number 2 minus B times current at port number 2. Let us say this in equation number 1. This is how the ABCD parameters are represented. They are representing voltage and current at one port relating with voltage and current at other port. So similarly, we can write I1, that is a current at port number 1, same CV2 minus DI2, right? So how in terms of matrix representation this can be written then? In terms of matrix representation, V1, I1, this can be written as ABCD parameters A, B, C and D, and the output variables V2 and minus I2. So here this is the input variables, this is the output variables V2 and I2, and this is how the representation of voltages and currents using ABCD parameters. Okay, so for symmetry and reciprocal network, or we could say if this two-port network follows the rule of symmetry and reciprocity, then what we can do is we can write A is equal to D. We can write in this way. And we can relate AD minus BC is equal to 1. Okay. So this is only applicable when we consider that this two-port network is symmetrical and reciprocal. Okay. So when it satisfies the property of symmetry and reciprocity, it will fulfill the condition A is equal to D, and this equation AD minus BC is equal to 1. Okay. So this is how the simple representation of a two-port network in terms of ABCD parameter. Let us go ahead. So next, we are going to see image impedance and transfer function of two-port network. Okay, image impedance and transfer function of two-port network. We already saw this in a brief whenever we saw this foundation theory of image analysis, image parameter analysis. You just recall from equation number 10 and 11 that how we conveniently represented Zi1 and Zi2. Those are finally expressed by equation number 10 and 11, showing that they are written in terms of transmission parameters. Okay, so we go ahead from this point now, because this has been already discussed how the image impedances are expressed in terms of transmission line parameters. Yes. Now the next is, as I already said over here while discussing this particular part, that is the configuration of the filters. Okay, configuration of the filter in terms of T or pi network. So this is a typical T type configuration, right? And this is a pi type configuration. It depends on how you people start to design. Whenever you want to take the first element as a series, you need to take the T type configuration. And whenever you people want to start with parallel element first, then you need to stick with pi type of a network. Okay, so these T type and pi type network model representation as a basic building block of image parameter filter are already discussed. Okay, so they can be related with the impedance parameter also. So both, that is the T parameter and T type section and pi type section, right? So we go ahead. Constant K section filters now. Okay, so this is the basic building block of image parameter filter design. Constant K section. Now this is an important aspect. I will change the color. Constant. Say we are dealing with now image parameter technique of filter synthesis, for which constant K sections are the basic building block. Constant K section filters. Remember that this is the basic building block of filter using image parameter technique. Image parameter technique. Please remember. Okay, constant K section filter. Now we are going to have the details on how to design constant K section filters. This is the basic building block. Okay. So transfer function, how in general we can write the transfer function? Transfer function is simply given as ratio of output response to the input response, right? In general, the transfer function is given as output response to the input response. If we apply the same to the voltages, V2 is the output voltage, V1 is the input voltage. So in terms of ABCD, how it can be written? If you analyze, you will get AD minus BC multiplied by into another square root D by E. Let us call this equation number 1. So transfer function expressed in terms of voltage ratio is given by equation number 1. And similarly, transfer function, when it is represented as a ratio, I2 divided by I1. Okay, so this can be written again as same AD minus BC into another square root of A by D now. Call this an equation number 2. Okay, and how the propagation constant is given? Propagation constant in the real propagation direction. Propagation constant. How it is given? The propagation constant is given as e raised to minus gamma, and how it is represented? Just recall, it is AD minus square root BC, equation number 3. Okay. So with the reciprocity property again, with reciprocal property, with reciprocal property. What we can write? With reciprocal property, we can write the equation AD minus BC is equal to 1. Therefore, from equation number 3, what we can write? The real part cosine hyperbolic function of a propagation constant gamma, we can write it as a square root of AD. Let us call this an equation number 4. So equation number 1 and 2, they are specifying the transfer function, ratio of output to the input, either in terms of voltage or in terms of current. And equation number 4 indicates the propagation behavior. Okay. So a prototype T network and pi network for the constant K section filters, now we are going to design. Okay. So for T section constant K filter, so here I will write the T section. So here I will write now how the T section is represented for constant K section filter. T section, T is one type of filter representation for the constant K. Okay. So here we need to start with a series element. Then we have a shunt element. And then again a series element. So this is a T-type configuration, right? So here the impedances we will get Z1 by 2. This is a standard calculations of image impedances Z1 by 2, Z1 by 2, and this is Z2. Okay. And similarly for pi type of network, pi section, constant K, how they are represented. First element is the parallel element. Second element is the series element. And third element is again a parallel element. Okay. So here the value of the first element is 2Z2, while this is Z1 and this is again 2Z2. Okay. So the characteristic parameters of T section and pi section constant K type filters are shown in front of you. Okay. So here T and pi equivalent representation of the two-port network which present the filter is considered for transmission line parameter. For low pass configuration, series impedance is replaced with inductors. Okay. So for low pass filter, series impedance in the arm, series impedance represents inductor, right? Series impedance represent inductors, and shunt impedance are represented by capacitors. Okay. In the case of high pass filter, if you want to design a high pass filter, then you need to interchange the series arm impedance rather, is represented as capacitor, which is opposite to that of the low pass filter configuration, and the shunt arm impedance is then represented by the inductor, opposite to that. Okay, so this we need to remember. Whenever we want to design a low pass filter, series arm impedance is to be designed with the inductor. Okay, and shunt arm impedance is designed with a capacitor. And whenever we want to design a high pass filter, directly opposite process we need to make. Okay, so we need to write the low pass T section for low pass T section filter. Okay, so we consider that this particular T configuration we want to design a low pass. Then the first impedance Z1 is to be given with the inductor J omega L. Okay, and similarly Z2 is the parallel element which is to be given with j omega c, 1 upon j omega c capacitor. Okay. Therefore, T section impedance ZIT, T section impedance will become under root L by C 1 minus omega square LC divided by 4. Okay. So this is the low pass T section. Okay. Say whenever DC signal, in the case of DC signal, for DC signal frequency is 0, that means omega will become 0. Omega will become 0, right? Omega square LC, it will become 0. Okay? And this can be written as simply Z0 is equal to under root LC. Okay? This is when the frequency is DC frequency. And how the cutoff frequency is given? Cutoff frequency is given omega C is equal to 1 upon 2 under root LC. 1 upon 2 under root LC. Okay. So these equation you need to remember because these will be required in order to design constant K section filter. Okay. Similarly, for high pass counterpart of the T section, for high pass filter, for high pass T section, we need to simply reverse the position of inductors with capacitors and capacitors with inductors and vice versa. So how the Z1 is now then given? Z1 is given as 1 upon j omega c. See here, simply we are interchanging this with this. And how the Z2 is given? Z2 is given as a j omega L. Okay. And in this case also we should get omega c is equal to 1 upon 2 under root LC only. So these are the design equations of low pass T section and low pass and high pass T section. Okay. So how these are then represented? Okay. So I will draw here the all possible configurations of T section and pi section. First of all, T section low pass. T section low pass. So in the series arm, it should be an inductor. In the parallel arm, it should be a capacitor. It is so simple in this way, right? So this circuit will act as a filter device in T configuration or in T section, which will give us a low pass behavior. Okay, and this has to be L by 2, L by 2 as discussed over here in this configuration. Okay, and similarly here, what we are going to write is a capacitor C. Okay, so this is the low pass T section. Similarly, how the pi section is represented? Pi section low pass circuit. So how it is given? First element is a parallel, and in parallel it is a capacitor, right? Then an inductor as a series, and then again a capacitor as a parallel. See over here, see this one. Okay. So we need to replace parallel capacitors, series, inductors in the prototype. So this will be an inductor L. Now this will be a C by 2 and this will be a C by 2. Okay. So this is about low pass section. Now similarly, how we can draw the T section and pi section filters for the high pass counterpart? Again, T section high pass configuration, high pass filter. So what we need to do is simply interchange the position of capacitor with inductor and vice versa. So first element is now capacitor. Second shunt element will be an inductor. Third element series is again a capacitor. So what we did here, we replace the position of inductors and capacitors with vice versa. Okay, and this is the value of capacitance is 2C, this is also a 2C, and this is the L. So this is a T section high pass filter. And similarly for the pi section, I will write over here the pi section high pass. So how it is given? Pi section high pass. First you need to start with parallel element. So for the parallel element for the high pass configuration is a inductor. Then series element is capacitor, and then again a parallel element inductor. Okay. So the value of this capacitor is C, the value of these inductor is 2L. Okay. So T section low pass, T section high pass, pi section low pass, and pi section high pass. So these are the possible configurations available for designing constant K type filter sections. Okay. And the ABCD parameters are represented in terms of Z1 and Z2. Okay. So more about designing of constant K section filter and the implementation of first constant K section image parameter based filter. We will take a typical design example in our next lecture and will demonstrate you how to design constant K section filter as a basic building block in the procedure of image parameter filter synthesis technique. So I hope we have gone through much more information today, starting with our first model. Okay. So just I will revise whatever we have done so far. So already we started with the concept of a filter. What is a filter? And we have illustrated you the uh, physical concept. What is the filtering process or the filtering mechanism? Historical development of the filters we have gone through. We have seen what exactly the frequency response of the filter is meant, the four types: low pass, high pass, band pass, and band stop. Then ideal characteristic and the actual characteristic. Then we discussed about the periodic structure, what are their importance and how they are useful in the construction of filters, how they are represented by a unit cell. Then we discuss what will happen when we terminate the periodic structure, the reflection coefficient concept, and the passband and stop band properties exhibited by the waveguide parameters. Then we came to the classification of the filter in terms of passive and active components. We discussed what are the different filter parameters with which the characteristics of the filter is specified. We defined them all, especially the insertion loss and the return loss. And then we started with filter design methods. So we saw and differentiated between two distinct methods. First is the image parameter method and second is the insertion loss method. And we just started implementing the filters by using image parameter technique. Okay. So image parameter filter design principles we explained in terms of transmission parameters and we related image impedances with them. And then we saw the constant K section filter prototype as a basic building block. And finally, we have taken down the filter configuration for the two possible sections, T section and pi section. So more about how to design constant K section basic building filter block for image parameter technique that we will cover in our next week lecture. So I hope you have gone through this. These videos will be saved and at any time you can refer them back and you can prepare for the module. Okay, so we'll stop over here and again in the next week we will proceed further for the actual design operation. So what we studied today is mostly a theoretical foundation of filter theory. Okay, so thank you very much for giving the time and for being with me for this 3 hours. So again, I hope I will definitely see you people in our next lecture. So thank you very much, and I will stop over here. Thank you very much.